12, 101. So, chapter 12, problem 101. All right. So we have mercury. Mercury is used in barometers since it has such a low vapor pressure. The heat of vaporization of mercury is 59.2 kilojoules per mole. 59.2 kilojoules per mole. And its normal boiling point is 629.9 Kelvin. That means its boiling point, and we can use this equation. What do we call that equation? The Clausius-Clapeyron equation. All right, on page 577, in which we have the natural log of pressure 1 over pressure 2 equals delta H of vaporization over gas constant R times 1 over temperature 2 minus 1 over temperature 1. All right, so this relationship here is the relationship between the vapor pressure at different temperatures. Okay? So, let me see this here. Okay. Okay. So, pressure 1. Well, they're asking for what? The pressure at okay, so looking at the temperature, what is the vapor pressure of mercury at 298.2 Kelvin? So this is pressure 1 up here, temperature 1. It's at, let's see, what does it say the temperature 1 is? What's the normal boiling point is 629.9. So this is 629.9. 629.9, and that's at atmospheric pressure, so it's 1 atm. And what is the, so when it says normal boiling point, that means the boiling point at atmospheric pressures. And under atmospheric pressures, the vapor pressure of the liquid is 1 atmosphere. Okay? So the vapor pressure of mercury is 59.2 kilojoules per mole. That's here. Its normal boiling point is 629.9 Kelvin. What's the vapor pressure at 298.2? So 298.2, and we want to know the vapor pressure, second vapor pressure. Okay, so calculator. Okay, so here's the calculator, 1 over 298.2. So I'm going to solve this fragment here first. Minus 1 over 629.9, and I'm using parentheses, right, get the order of operations right, so I'm getting here 0.0017659. Oh, this R value. You have to use an R value that's going to allow these units to work. So this is 1 over Kelvin here. This is kilojoules per mole. This is going to be in atmospheres. So this units are going to be canceled out over here. So these units need to cancel out over here. So our R value, let's see on page where they show the equation to be used. Page 553. We see the equation there, and 552, we see the R value, 8.314, and that's joules per mole per Kelvin. 8.314 joules per mole per Kelvin. So we have to convert this to joules then, so that's going to be 59,200 joules per mole per Kelvin. So So now we have per mole per Kelvin, and so all of these are going to cancel out. All right, so we have this value here, which is this part, multiplied by 59,200, divided by 8.314. All right, so on this side, I'm getting 7120.5 after I've taken this value, multiplied it by 59,200 and divided by 8.314. So 7,120.5, and that equals the natural log of this entity here. But what I'm going to do, when I have natural log divided by natural log, that's the same as taking the natural log of 1 ATM. Let's see, minus the natural log of our pressure there. So that is how we handle natural logs when we have a variable in that natural log, right? Now the natural log of 1. What's the natural log of 1? That's 0. And so that drops out. So the negative natural log of P will be 7,120.5. So if I take I need to take the I need to raise e to the value of both sides to get rid of this natural log thing. Then I would have, and I guess I can move that negative sign over first to take care of that. Well, let's see, am I going to be able to do that? E second natural log to the $7,124. Try it again. Natural log of 7,120.5. Did I get that wrong? Oh, maybe I made a mistake here. $298.2. 629.9. Let me try that again. Make sure I didn't make a mistake. 1 over 298.2 equals 0.03353. 1 over 629.9 equals. All right, so I got 0.00158. So I take 0.003353 minus 0.00158, and that value is 0.0017659 times 59,200, right? Divided by 8.314. Oh, well, this time I got 12.57. So, all right, so 12.57. Let's see, so I take the raise e to the 12.517. E to the 57. E to the negative 12.57. Oh, so we bring this negative sign over first by dividing both sides by -1. And then we take the e to the ln P2 equals e to the negative 12.57. E to the ln P2 equals pressure 2, and this e to the negative 12.57 is 3.475 times 10 to the -6. All right, so that should be the what? Vapor pressure at 298 Kelvin, right? Is that right? Let's see. Yeah. So what's the vapor pressure at 298 Kelvin? 12,101. 3.46 times 10 to the -6 atmospheres. Yeah. All right. Good. 12,103. can determine the heat of vaporization by using that same equation if we know the vapor pressures of a substance at two different temperatures. Determine the heat of vaporization of diethyl ether if the vapor pressure is 1 millimeter of mercury at minus 74.3. So we have 273 minus 74.3, that'll give us the Kelvin, 198.7 Kelvin. And what's the other temperature? 18.7, so 273 plus 18.7, 291. All right, up here we can determine the delta H of vaporization. It's energy of vaporization, 8.314. This is going to be, again, the units of kilojoules per mole Kelvin. All right? So that's going to have units of kilojoules here. This is going to be, we need to convert that 1 millimeter into atmospheres. So 1 divided by 760, 0.0013 13158. Now that'll be in, let's see, if we have to do that. I guess we don't need to do that conversion because we don't have any units of, it can be 1 millimeter here, and then the units, well, let's see, what's the other one? The other vapor pressure, 425. Yes, we don't need to convert that. So the natural log of that value here. All right, so we can take 1 over 425, and then we can take the natural log of that value. All right, so I'm getting negative 6.05. Let's move that down just a little bit. All right, equals 1 over 291.7 minus 1 over 198.7 so I'm getting negative 0.001604. All right, I can bring it over here by multiplying both sides by that negative 0.001604. All right, so delta H of vaporization all over 8.314, right? So to get delta H vaporization by itself, I multiplied this value here. Or I took this value, divided it by this value, and now I'm going to multiply it by 8.314. And that gives me 31,359. And that should be in joules. Oh, this isn't in kilojoules, sorry, this is in joules. Joules, and so joules per mole. So, let's see if we're right. What number are we? 12103? 31,400 joules per mole. Okay. (12.105). Sketch the phase diagram for a substance that has a triple point at minus 15. So here's the temperature down here. Here we'll say is minus 15. There's the triple point. At minus 15 degrees Celsius and 30 atmosphere, or 0.3 atmospheres. So here is our 0.03, 0.03? 0.30. And it melts at 10 degrees minus 10 degrees Celsius. So 15 minus 10 would be up here. And that's where its melting point is going to be, right? But it melts at minus 10 and what was the pressure? 1 atmosphere. So 0.3, so 1 atmosphere, we'll say it's up here. So here's our triple point. Here's our melting point. This is probably going to come down here, and we're going to have another line going off here, right? Because this is where we're going to have our solid. This is going to be our liquid. And this is when the temperature increases and the, oh no, sorry, this is our liquid. And this is our gas. Right here, under these conditions, when the pressure is really low and the temperature is increasing, that's our gas phase, right? If you take a gas and you increase the pressure, so this is pressure, this is temperature, take a gas, you increase the pressure, it turns into a liquid. You take the liquid and you decrease the temperature, it turns into a solid, right? All right, so solid, yeah, that's right. All right, so let's check that 12105. All right. What did it give us? Another value? 12105. Oh, has a normal boiling point at 90 degrees Celsius. So I didn't see that. So normal boiling point. So that means that 1 atmosphere again. This goes out to 90, and this comes up to here. So it doesn't necessarily need to be curved. It's probably going to be curved, but there's no indication to us that it would be curved, but it probably will curve. But I missed that point right there. So it has a normal boiling point. That means at 1 atmosphere pressure at 90 degrees Celsius. All right, 12107. According to figure 1231, what phases should exist, phases should exist for carbon dioxide at minus 60 and 6 atmospheres. So let's turn to 1231. There it is. So of 107, we're looking at figure 1231. It's a phase diagram for carbon dioxide. The interesting thing about carbon dioxide's phase diagram, right, is this line between solid and liquid slants to the left, right? So there can be conditions in which the solid sublimes to a gas. Well, it always can, but at room temperature, 760 torr, at room pressure, 760 torr, and room temperatures, you get the solid converting to the gas. Anyway, let's see, what question did they ask us here? 12107, according to the figure, what phase should exist at minus 60 degrees Celsius and 6, minus 60 and 6 atmosphere. 6 what? 6 atmospheres. 6 atmospheres. So at minus 60, we're going to be behind the triple point, and at 6 atmospheres, we're going to be a solid, right? Minus 60 and 6 atmospheres. Well, that line, it doesn't necessarily determine where it intersects at, so I'm not sure. How we're sure it's not quite a liquid yet. But I think they're just trying to say very high pressures. So we would expect it to be a solid, that's right. Minus 60 and 2 atmospheres. 2 atmospheres, we would still minus 60 and 2 atmospheres. Oh, I'm looking at the wrong one. Sorry, I'm looking at, I was looking at 1229. Sorry, this goes this direction. There we go. So 1231. So yes, it's clear to us there at 6 atmospheres, we're going to be solid. But at 2 atmospheres at minus 60, 2 atmospheres at minus 60, it's going to be in a liquid phase, right? Because it's 2 atmospheres is right down there, minus 60. Or sorry, gas. Right? Let me double check here. Minus 60 degrees Celsius and 2 atmospheres. Minus 60, which is right here, and 2 atmospheres. Yeah, so it's going to be a gas. Then C, what's C asking? Minus 40 and 10 atmospheres. So minus 40 is over here, and 10 atmospheres, that's going to be a liquid. What's the other one? Minus 57 and 5.2. Minus 57 and 5.2. It's going to be the triple point. So it's going to be solid, liquid, and gas. Okay. That's 12,107. So in this range, it's solid, liquid here. If it's right there at the triple point, it's solid, liquid, and gas. Okay, so that's 12,107. 12,109. How many zinc sulfide ions are present in the unit of a zinc sulfide cell of zinc sulfide? 1242 is the figure that they refers to. .1242. So the question is, how many zinc and sulfide ions are present? 1242. So there are 1, 2, 3, 4 zinc ions. So let's draw this thing out first. All right. Okay, so we have, let me do a different color here. So we'll have our sulfides, black. One of our zinc is red. Okay, so we have a sulfide here, here, at every corner, right? Sulfide at every corner, and one on this face. So if I cut this front face in half, there's an atom here. There's one on this face here. There's one on the, see this back face over here? There's one over here. This left face, there's one over here. This top face, there's one here, and the bottom face, there's one there. Now the unit cell is just on the inside, what's on the inside of this square. So on the inside, this atom, which is on the face, only has half of it on the inside. So this represents half of an atom. This represents half of an atom, the one that's front and back, or left and right, depends on how you want to see it. This one here represents half, and that one represents half. So for each 2 faces, there's one whole atom. So there's one atom there, front and back, 2, and top and bottom. So there's 3. So there's 3 sulfurs from the faces, because there's a total of 6 faces and a half face for each sulfur. And each corner provides a quarter of an atom, right? Because if I think of this sphere on that corner, only a quarter of it is going to be inside. So this represents one whole atom, and the bottom ones represent one whole atom. So that's a total of 2 sulfurs due to the corners, right? So there's a total of 5 sulfurs. That's a 5 there, 5 sulfurs. And then we see the zinc atoms. They are not on the surfaces or on the edges at all. They are, there's 4 of them, and they are within these spaces in here. So there's going to be 4 zinc atoms and 5 sulfur atoms in a unit square there. Is that right? 1, 2, 3, 4. 1, 2, 3, 4, 5. And those are face-centered That's a face-centered lattice. Okay, so that's the zinc fluoride, 12107. Let's see what they say. Oh, this is 12109. Oh, they said we only have 4 sulfurs. 1, 2, 3. That's 1, 2, 3, 4, 3, 4, 5. Oh, no, sorry. This edge right here, if I take a sphere and cut it up like this, right, that's not going to represent 1/4 of the atom. That's going to represent 1/8. So this would be 1 atom, 2 atoms, and then each two faces would be 3. So that's only 4 sulfurs. 4 sulfurs and 4 zincs. Okay, good. So 12107, there's 4 sulfurs, or 12109, sorry, 12109, there's 4 sulfurs and 4 zincs. There's my book. All right, 12111. Atomic radius of nickel is 1.24 angstroms. Nickel crystallizes in a face-centered cubic lattice. What's the length of the edge of the unit cell expressed in angstroms and picometers? Length of the edge. So we have atomic radius of nickel is 1.24 atoms, and we have our face-centered cubic lattice. So in a face-centered cubic lattice, again, we can review that. Look on page, where's that? There it is. Page 362, 1238. Again, we have yeah. So again, we have our cube here, and we have 1/8 of an atom here. We have 1/2 of an atom here, so we're cutting it in half. You have another face here, another face here. Okay? So if they tell us that, what do they tell us? The atomic radius of nickel is 1.24 angstroms. We know that this here is, well, the radius is 1.24. So we know that this is 2.48, the diameter here. And this all the way down to there, plus that would be 2.48. So that would be 2.48 times 4.96 angstroms. And that's this length here, okay? So if this is a 90-degree angle, this is a 45 here, right? So we know that the relationship between this length here, and that length is, what is it? Square root of 2, 1 root 2, 1 root 2, right? So double check that. Where did I see that information here? Well, no, that's right. So if this is square root of 2 over 1, then we can get that ratio, right? This is 4.96 over x here, right? So, we're going to do it the other way. 1 over square root of 2 equals x over 4.96. Then we'll have x on top. So 1 divided by the square root of 2 times 4.96. So x equals 3.507, and that's the length here. That's the length of the side of the crystal. 12, 111. Let's check that out. 3.51 angstroms, or 3.51 picometers. Did they ask for it in picometers? Oh yeah, in picometers. Sorry, so when they ask for it in picometers, it's going to be 351 picometers, 350.7 picometers. All right, 12, 113. Potassium ions have a radius of 133 picometers, and bromide ions have a radius of 195 picometers. The crystal structure of potassium bromide is the same for sodium chloride. All right. Stop right here for a little bit.